All right, here we go. Let me pull up my thingy thing. Okay. So today we're going to cover a couple of things. Basic circuit elements. In fact, not even basic circuit elements, just one basic circuit element basically, which is a resistor. And I guess power sources. So there's standard ways we draw circuits here. I guess there's standard symbols you use to draw circuits. So this symbol I've drawn here is some sort of voltage source. Usually what you draw one line longer and one line shorter. The longer line is supposed to represent the positive terminal and the negative terminal, like on a battery, basically. Although if you're drawing a battery, I think it's more standard to draw like a long line and a couple of short lines to do a battery. That's a very minor point, I would say. So yeah, a battery could be a voltage source like this. You know what? I will draw the circuit in black. So then you draw the wire, and I typically like to draw my circuits kind of like, goodness, that's some terrible drawing there. Like this, sort of in a loop, like that. And along this loop, there'll be various circuit elements. You know, we'll get to them. We'll definitely not get to all of the different types of circuit elements, but just to show you what they are, the one we definitely are going to get to today is the resistor, which looks like a kind of a squiggly boy, like that. So that's a resistor. There's something called a capacitor, which we might get to later. I'm not sure if we really have time, but it looks like that. There's inductors, which are like a little squiggly guy, which I think usually inductors also have an arrow indicating the direction. There's all sorts of stuff. There's like diodes. I don't know if anyone's actually ever worked with electronics, but diodes are pretty interesting. Diodes are like little gates that only allow current to flow one direction. So in this diode, current would flow this way, but never backwards, which is pretty useful in circuits. Trying to think of other circuit. There's a bunch of other circuit elements that I'm sure I'm forgetting right now. Well, actually, redstone wiring is based on basic circuit elements. It's like having current going through a circuit. So in that sense, you know, it's not unlike that. I guess one difference is that these circuits need to be closed. So in this example, we have this circuit here with two lines. This guy here, this one. It's a, you know, I'll write the names. I'll write the names. Why shouldn't I? Capacitor, inductor, diode. And then, you know, there's other things like switches. You might have like a switch. Trying to think of other elements you might see in circuits. Sorry guys, I'm kind of tired right now, so my brain not work. Oh, I guess I should just write down voltage source. Or a battery. Literally can't think right now. But I think this is more than enough elements. I mean, we're not going to get to... Definitely not going to get to inductors or diodes this year. We'll see switches. We'll definitely use voltage sources or batteries. We'll definitely use resistors. We might get to capacitors. I'm not sure. I give it less than 50-50 chance. I think it's unlikely we get to there. Okay. So let's imagine we have a circuit. with a voltage source here. And you have a resistor. Really easy. We're going to call this V for voltage and R for resistance. In fact, I'll call it R1, even though there's no other resistors. And I'll call this V0 for original. So this is like the simplest possible circuit you could have. And essentially, what I'll teach you today is, I guess what I call, I'm not sure anyone else calls it this, but I call it this, which is solving a circuit. Circuit, I got to spell correctly. Circuit. Okay. So solving a circuit, when I say that, it means finding the values of voltage, current, resistance, and power dissipated for every single element in the circuit. So for this example, I would want to find the resistance. I guess it would be the resistance of the whole circuit. Sorry, I didn't mean to draw a line through the resistor there. It'd be the resistance through the whole circuit because there's only one resistor. The voltage between, this point and this point. Most of the time that would be given. The current going through this circuit, that would be really the current going through R1. And the power dissipated across R1. Some of these things need to be given. So, for example, I usually would give you V0. Let's say 12 volts, just as a random number. Okay. So I'm going to put 0 subscripts on all these, and that just means that I'm finding these values for the voltage source here, with V0 as being given. REFF is the next big thing we need to talk about. It's the effective resistance of the entire circuit. Now, with just a single resistor, that's all it is. It's just the value of R1. Let's say 4 ohms is the resistance. Then the effective resistance of the whole circuit is just the resistance of R1. If there were more than one resistor going on, which I'll show you next, it's going to be more complicated to figure out what the effective resistance of the entire circuit is. But with just one resistor, it's pretty easy. So here, REFF is going to be 4 ohms. So now we have enough information to solve for the rest of it. For the current going through the circuit, we use Ohm's law, V equals IR. So we know I and we know V, or sorry, R and we know V. So to get I, we just divide. I equals V over R. So current is going to be 12 over 4, which is 3 amps. Not so bad, right? So that's the current going through the entire circuit. And the power dissipated, there's a new equation here. Well, now this is why I should keep more detailed notes with me. I have them somewhere. I don't remember the name of this law. It's not really important. But this equation, P equals IV, the power dissipated across any given circuit element, is equal to the current through that element times the voltage across it. So I guess one way to think about this is like, let's say you had a light bulb. Old style incandescent light bulbs, like the ones with the filament, right? Basically all that is a really inefficient resistor that heats up a lot. So it has a big resistance, R, and probably a big current going through it, and regular wall voltage going across it, 120 volts. So the power dissipated in watts is like the brightness of that light bulb, right? Like a standard 60 watt light bulb that's how much power it's dissipating per or energy per second, I guess, joules per second. Just that's how much power it's dissipating. That's the whole idea, is that this light bulb is basically just a big resistor. So you could actually even draw the circuit of a light bulb exactly like what I've drawn here. So to use this new equation, power equals current times voltage. We know current 3 amps and voltage is 12 volts. So 12 times 3 is what, 36 watts? And that's pretty much all you need to do for this entire problem. This particular one, anyway. Not so bad. Any questions about it? About solving this really simple circuit? We're going to do a more complicated one next. No questions? It's good to hear. Just real quick, I'm going to check who's here. Oh, Sasuke's here. Hi. You didn't say hi earlier. I didn't see you. But I'm going to check off that you are here. Is anyone here in chat or in the channel that I have not yet made a green box for to show that I've seen you this week? Abby, Victoria, Isabel, Josh, Ashley, Savannah. Any of those people here? I'll assume, giving you enough time, that no, you're not here. Okay, let's move on to another example. And this will show you how to do multiple resistors in a single circuit. There's two different ways to do it. Maybe not two different ways to do it. There's two things you have to take into account, I guess. Okay, so let's draw another circuit with, God, I'm bad at this drawing thing. Why is it so, okay, there we go. It's hard to get straight lines. Okay, voltage, and let's put a resistor here, and another resistor here, and back to the voltage source. We'll call this V0 again. I'll call this one R1 and R2. And now I'm gonna draw out a table, basically. I'm gonna say V0, I0, REFF, and P0 for the original voltage source. I have slots for all those. I'm also gonna do like a table, basically. V1, I1. I'm gonna draw a straight-ish line here, if I can manage. Oh God, I am bad at drawing straight lines. Goodness. Good Lord. Sorry you have to watch my art struggles. Okay, all these things for each of the elements. And then finally V2, I2, R2, and P2. Okay. In this case, I'm going to need to give you some information before we start. So let's keep V0 the same, 12 volts. 12 is a really nice number. It's divisible by a lot of different things. And let's say R1 is 2 ohms and R2 is 4 ohms. Like that. I think that's enough information to actually figure this out. Okay. So solving circuits like this with these little tables is totally like doing puzzles. And if you really get into it and you need to do a few of them before you start kind of knowing what to do. So your first few, they're going to be a little bit of a struggle, but once you get used to them, I think most students have found them to be kind of satisfying to do because they're like these weird little logic puzzles that you have to figure out. And we'll do some more later on when we do the, we'll do a practice session after in a bit. In fact, I want to check before I go too much further, how much longer do we have in this class? We started at 10:30. We go to 11:40. Okay, so we got plenty of time. Okay. So, like I said, this is kind of like a little puzzle that we have to figure out. So we have two resistors, but the battery here, or the voltage source, whatever it is, doesn't really know that there's two resistors. It just sees that this circuit has a total net resistance, whatever it is. We call it the effective resistance. And we need to figure out what that effective resistance is. I've drawn a very simple circuit here with basically two resistors in a straight line with each other. There's no branching things, there's no extra places for electrons to go through this circuit. They're all just going to flow straight through one resistor, then through the other resistor. And this is what we call a series circuit. So the resistors are in series with each other. We'll see what the other option is called parallel circuits in just a moment. But this is a series circuit. So when resistors are in series with each other, meaning they're in a direct line, there's nothing in between, there's no branching, like extra places for stuff to go. That's in series. So the effective resistance in series of any number of resistors is just their sum. So you just add them all together. So in this case, the effective resistance of this circuit, since they're in series and they're in a straight line with each other, is going to be R1 plus R2. So 2 plus 4. Hopefully you can all do 2 plus 4. I'm going to assume that you can. 6 ohms is the effective resistance. So essentially what we're saying is that instead of this being a circuit with two resistors in series, like this, the effective resistance makes it a circuit with just a single resistor with the value of R effective. Kind of like what we had above here with just a single resistor. Whoops, and I should connect this. Right, and so now this makes it a lot easier to solve. To figure out I0, the current coming from our voltage source, which is maybe a battery or maybe a plug from the wall, we just do V equals IR, Ohm's law again. So V equals IR, I is going to be V over R, so 12 over 6. We're going to get 2 amps as our current there. We can do power as well. P equals I, 2 amps times V, 12 volts. We're going to get 24 watts. Okay. Here's where we get into some of the so-called circuit rules. And again, this is a nice simple example to start with. We have a single path. So imagine electrons are flowing through this path. Now, I've drawn it going this direction because that's the circuit convention, going from positive terminal to negative terminal. But we all know that really, in reality, the electrons are flowing the opposite direction. It doesn't really matter what direction we choose right now. It's just true that there's one loop around this circuit. If I drew a more complicated circuit, right, like we'll deal with in the next one, which has a loop here and then another loop here, and a complete loop like that. These loops are going to become really important, going from the positive terminal to the negative terminal of our battery or our voltage source. These loops are going to be really important. For now, there's only one of them, which is actually super helpful to us. So the next thing we can deal with here is going to be current, I1 and I2. So because there's only a single loop, there's no branching extra places for current to go. If we imagine current as what it really is electrons flowing, as long as there's no place for it to split, that current is going to stay the same throughout the entire circuit, right? You can imagine that, imagine it like water flowing through a hose, I guess. If this loop is closed, the amount of water flowing through is not going to change anywhere. If it branches like this, and sorry, branch, I'm going to use your name a lot because there's branching going on. If it branches like this, you can imagine the current in this part of the circuit is going to be maybe different than this part. But since there's no branching, it all stays the same. So the current on a closed circuit like this is going to be exactly the same all the way through. There's nowhere else for it to go. So there you go, 2 amps all the way through. You're not splitting up the current. Which means now I can actually use Ohm's law to calculate the voltages for V1 and V2. So V equals IR. 2 times 2 is going to be 4 volts, and 2 times 4 is going to be 8 volts. I want you to notice something, that 4 plus 8 is equal to 12. That's not a coincidence. One of the laws for circuits is that voltages on any given loop, any single closed loop around the circuit, any closed loop. So in this branching example, this here is a closed loop, but also this here is a closed loop as well. So any voltages on any closed loop, all of the voltages have to add up back to the original voltage. So in our case, V1 and V2 are the only two on this closed loop, so they have to add back up to V0. If we had a branching one, which we're going to have next, it'll show us that different loops will have different voltages. Okay. So then also we need to calculate the power. P equals IV, so 2 times 4 is going to be 8 watts, and 2 times 8 is going to be 16 watts. And again, I want you to notice 8 plus 16 is 24. This is another rule for circuits, which is that all of the powers, no matter where they are, every other power, P1 through, if you have 30 things, P1 through 30, add them all up, they have to add back up to the original P0. Doesn't matter where they're placed in the circuit, how they're connected, as long as they're in the circuit, all the powers add back up to the original power, which is pretty cool. Okay. How we feeling? We feeling good? Feeling happy? Content? Confused? Whatever you're feeling, I'm going to move on to the next part. We want to do also, so we've done series circuits, now we want to do parallel circuits. And don't worry, I saved that page, I'll upload it later. Okay, parallel circuits. So again, we're going to start with a V0 voltage source of some sort. Could be a battery, could be plugging into the wall, could be, who knows, something. And instead of having resistors in a straight line with each other, we're going to have now branching circuit that has two different places, two different routes that electrons could flow through. So I'll draw these routes in here like this. So here's one complete loop around the circuit. But here is another complete loop around the circuit, totally independent. So there's two different completely, and you know what, I'll have to label these real quick. R1, R2. So solving this circuit is going to be a little different than solving the last one. I'm going to do the same table kind of thing. Equals signs for all these bad boys. Goodness, I am bad at drawing straight lines. It is kind of shocking how bad I am at drawing straight lines. P2 equals, okay. Most of the time, all I'm going to need to give you is V0 and the resistances. What's a good number? Let's make this 4 ohms. And what should this one be? These are actually, I want to make these actually nice round numbers, so I don't have to pull out a calculator. So I had to do some figuring in my head before I can really get to these. Give me a second. It takes a second for me to come up with something that'll make a nice number here. Especially doesn't help that I got up super early this morning after not getting much sleep, so brain is super foggy. What is that? No, that's not nice. Oh, you know what? I'm not going to do 4. I'm going to do 6 ohms. I'm going to do 3 ohms. I think that should make it a nicer number. Okay, so this is called parallel resistors. No. P does not look like an R. Parallel resistors. That means when there are two parallel branches. They're not in straight line with each other. They are alternative places that electrons could flow. So at this junction here, I'm going to call this a junction, where the two pieces of the circuit branch off. The amount of current, I0, flowing through from the voltage source goes here. It then splits into two parts, which we're going to call I2, because it goes to resistor 2, and then I1 here. I1 plus I2 coming from I0, splitting off at this junction, they have to add back up to I0, right? No current is going to be lost here at this junction. It just splits into two different parts. So these two parts, which I'll call I1 and I2, need to add back up to I0. And when they come back together here at this other junction, they're going to come back and re-add to I0 again, coming back into the voltage source, which is kind of nice. It helps us keep track of it anyway. Again, you can think of it as like water flowing through a hose, right? If you have a hose branch, the water is going to go one of either two directions. So the amount of water total between the two branches does not change. It just splits up. And then when it rejoins here, it comes back together. Adds up pretty nicely. So that being said, when we have parallel resistors like this, the rule for finding the effective resistance of any number of resistors in parallel with each other is kind of weird. It's 1 over the effective resistance is going to be equal to 1 over R1 plus 1 over R2 plus 1 over R3, and so on. Now, the biggest thing most people forget, and I'm sure you guys are going to forget this at least once, is that this is not REFF. It's 1 over REFF. People usually, they'll do this part correct, and then they'll forget they need to invert what they get after this. So this usually turns out to be problematic. So in our case here, we're going to get 1 over REFF is going to be 1 over 6 plus 1 over 3. Remember, 6 and 3 are our two resistances here. So what's this? This is 2/6 plus 1/6. So 1/6 plus 2/6 is 3/6, which is really actually equal to 1/2. And remember, 1 over R effective is equal to that. So really this R effective is 2 ohms. I hope I didn't do that too fast for you guys. This is being recorded in a video, so if you need to come back and see it again, it'll be up on YouTube in a bit. But that's a basic example of how to do parallel resistors. Sound good so far? Because now we can solve the rest of the circuit. For the voltage source, for all the zeros, we can straight up go through and do Ohm's law here. V equals IR. I equals V over R. Doing some algebra. So 12 over 2. Current is 6 amps coming out. Power is IV. 6 times 12 is a number that I can't remember right now. I'm honestly too lazy to do it in my head. It's 72. So the total power dissipated by this circuit is 72 watts. There you go. Okay. Now, we're kind of stuck, though, because last time we knew, in the last one, we knew that the current going through a single loop of the circuit couldn't change. So we knew it had to be the same in these two, I1 and I2. But now it branches, and we actually don't know how much current goes through each one. Right? It'll actually be proportional to the resistances, but that's really not the way we want to figure this out. So there is another way to figure this out, which is another rule. This one has to do with voltages. So in the same way that all the currents around a single loop had to add up to the original current, all the voltage... Why do I keep hitting that? All the voltages around a single loop. So now go back to this red loop here. This loop around the circuit, this complete loop around the circuit, all the voltages on that loop, which in this case is just R1, or V1, I guess, all those voltages have to add up to the original voltage. So in this case, there's only two resistors, there's only two voltages, and one on each loop. So these two voltages, V1 and V2, have to be equal to each other. I guess that's another way to put it, is that voltages for elements in parallel with each other are equal. So in this case, V1 has to be equal to V0, because there's no other voltages, and all the voltages on a single loop have to add back up to the original, so V1 has to be 12 volts. And same argument for V2. It's the only voltage on that entire loop of the circuit, so it has to add back up to 12 volts, the original. Which is super nice for us, because now we can do V equals IR, and I equals V over R, so 12 over 6 here is 2 amps going through this one. And there's two ways to find this one now, I2. We could do V equals IR again, and solve for I, and that'll get us 12 over 3, which is 4 amps. Or we could say that, okay, the entire current was 6 amps, 2 of it went onto this branch, the rest of it has to go on the other branch, so 6 minus 2 is 4. So either way, we get 4 amps going through that circuit element. Again, I feel like I went through that pretty fast. I'm hoping you guys are keeping up. If I'm not, just tell me to slow down in the chat and I will do my best to pay attention to it. Finally, the power dissipated, just P equals IV again. 2 times 12 is going to be 24 watts, so P equals IV. And then P equals IV again. 4 times 12 is going to be 48 watts. Remember, 48 plus 24 is going to be equal to 72, which is again the original power. So everything worked out, you guys. We all so happy. How you feeling? We've gone through series circuit, parallel circuit. We're going to do some more practice problems a little bit later. But there's one more new thing I want to show you before practice problems. Branch is good. Does branch speak for all? I guess branch speaks for all. Does that mean you're electing him your president next year? Good. Branch does not speak for Saskia. She speaks for herself. Very good. I'm going to show you one last new thing, and then we're going to do sample problems. This final new thing is the idea of resistivity. So remember how I showed you that little actual resistor last week? Like a little peanut looking guy? I think the ones that I have are blue. And they had these little colored stripes on them. They were all different colors. So actual physical objects are resistors. And we're going to model our resistor. Actually, we're going to model them as cylinders. For the most part. Because that's the easiest geometry to do. So any individual object is going to have some resistance. It might be very, very small for really good conductors. It might be very, very large for really good resistors. Like plastic or rubber are really good resistors, so they have very high resistances. But I guess that's more of a property of the material itself. And that property of the material itself, which is not like the specific object just due to the material, we call resistivity. And the variable for that is a rho, a Greek rho, which looks kind of like a curvy P. So resistivity is just a property of the material. I'm trying to think of an analogy of something we've seen before. How about spring constant? So like a spring constant K is a property of an individual spring, right? Every spring, no matter like, it could have different size, shape, material. Every spring has a unique spring constant. That's more like the resistance, R, that we've been dealing with. So every individual resistor, even if they're made out of the same material, might have a different size and shape, and that gives it a different resistance. And the material has its resistivity, which contributes to that. And the formula for this is, it's on the homework here, actually. It's on the sidebar here. The resistance of any object, any physical object, is given by its resistivity times its length over its cross-sectional surface area. So in these cases, let's take these two cases, like a square cross-section and a circular cross-section. So this is like maybe a cube or a rectangular prism, and this is a cylinder. For the cube, the surface area, the cross-section is basically a square. You just take a slice through it at some point, and you get the area of that. So in this case, it would just be, height times width, right? For the cylinder, it's going to be a circle. Anyone know what the area of a circle is? I always ask this every year, and I'm amazed by the answers. Pi r squared. Right, so we're going to assume most of the time, unless I state otherwise, we're going to assume a cylindrical geometry for most of these. So the area, A, of this resistor cross-section is pi r squared. Thank you, Aviva. And then the length is just going to be how long it is. I guess I'll call it a script L there. Good. So the resistance for this kind of a resistor, a cylindrical one, is going to be, whatever the resistivity is from its material. We'll look up a table in a second. Times the length over the actual cross-sectional area of that circle. So we'll say length over pi r squared there. And that'll give you the resistance of an individual resistor made out of this material from rho. And it's worthwhile to look up a table of resistivity. I'm kind of wishing that I had actually looked one up beforehand, so I had one ready. But it doesn't take very long to Google it. Oh, here we go. That's not so bad. This problem has been solved. Good to know. Here are actual resistivities. The really weird units they're giving here should be ohms times meters. Would be default for us. Ohms times meters. They're giving it in micro ohm centimeters, which is odd to me, but whatever. You can see silver is actually silver, copper, gold, pretty conductive, very small resistivities. We're talking about micro ohms, whereas these are all good conductors. Oh, these are all pure commercial metals. That's not very helpful for us. We want the full range. That is not what I'm looking for. This is where it would have been really nice to actually look it up beforehand. Here we go. Here's an actual table. Here we go. Yeah, okay, so silver. There we go. Even the right units. Ohms times meters. Silver, really tiny. 10 to the minus 8 ohm meters. Copper, gold, aluminum, tungsten. These are all good conductors. Carbon is a lot worse. So we're going from 10 to the minus 8 up to 10 to the minus 5. So that's a 1,000-fold increase in resistivity. Germanium, silicon. Silicon is a nice like intermediate. Germanium and silicon are nice intermediate values. Whereas like glass and rubber and sulfur and quartz, fused quartz, are really high values for resistivity. Those are really good resistors. Insulators, you might even say. Whereas like the guys in the middle here, like germanium and silicon, you'd call those semiconductors because they're not super great conductors, but they're not super terrible either. And semiconductors are extremely useful because they have really advantageous properties. A lot of our modern society is built on the use of semiconductors. So yeah, there you go. There is a nice table of resistivities. Don't worry, I'm not going to ask you to memorize these. These are going to be given. There's also this matter of temperature coefficient of resistivity. So the resistivity of an object changes with temperature. I'll give you a formula for that, I think, next week. This week, don't need to worry about it. So you can see those resistivities. I'll write down here on this sheet of notes, the units of resistivities are ohms times meters. Just so we remember. Okay. That's all the new material I wanted to go over. I'm going to stop this feed and restart it so that I can have separate videos for lecture and problems.